Hello class, welcome to the STAT 215 Lecture 21 video. In this video, we are going to focus on 4 objectives. First, we're going to motivate the process of hypothesis testing. Second, we are going to define a null and alternative hypothesis. Third, we will define a p-value. And lastly, we will define type 1 and type 2 errors. Let's begin by looking at our first objective. Hypothesis testing. You may be familiar with the concept of hypothesis testing from your science courses. Let's talk about what it means in the eyes of statistics. For us, a hypothesis is a claim about a population parameter, such as a population proportion p or a population mean mu. A hypothesis test is a standard procedure for testing a claim about a population parameter. Let's take a look at a motivating example. Casting ingots. In ingots, which are huge pieces of metal made in a giant mold, as liquid metal cools, cracks can develop on surface, which makes it unacceptable for manufacturing certain parts. So therefore, it must be recast. For one plant, 20% of ingots have cracks and need to be recast. So the manufacturer decides to implement a new process. Out of 400 new ingots, 68 have cracks, which is 17%. So for us, we must ask ourselves, is this new method better than the original method? So in this situation, our population is going to be all ingots produced using our new method. Parameter P is the proportion of ingots with cracks in the population. Our sample is the 400 new ingots we are checking for cracks. Our statistic, p hat equal to 0.7, is going to be the proportion of ingots with cracks in the sample. This brings us to our second objective, to define the null and alternative hypotheses. So for statistics, when we state a hypothesis, it is a two-line hypothesis that contains a null and alternative hypothesis. The starting hypothesis to be tested is the null hypothesis. The null assumes that there has been no effect. We denote it as H naught, which is a capital H with a lowercase 0. How do we write it? We write H naught, semicolon, our parameter of interest, equivalent to our hypothesized value. In our ingot example, we would write H naught, colon, P equal to 0.20. The alternative hypothesis, our second line, proposes what we should conclude if we reject the null hypothesis. In other words, we would write this as capital H sub 1, or H1, colon, our parameter of interest. Now, what is going to be an option is it will be either not equal to, less than, or greater than our hypothesis value. In our ingot example, our alternative hypothesis would be H1 colon P does not equal 0.20. Now, how different to convince us? So yes, we have our values, but how do we tell if it's actually different? We can clearly see that 0.17 and 0.20 are not identical, but are they so different? Well, how can we tell? Well, let's think about this. What if the new cracking rate had only been, say, 19.8%? Well, that's very close to 20%, which would probably tell us that this is just likely a random chance and they're not actually significantly different. But what about a 1%? Well, that would be extremely unlikely that this could happen by just some random chance. This leads us to talk about our standard deviation of our sampling distribution of p hat. If you recall, the standard deviation of p hat equals the square root of pq over n. Using our ingot example, that would be the square root of 0.2 times 0.8 divided by 400. That would equal 0.02. If you think back to your 68, 95, 99.7 rule, you can remember that 68% of your information should lie within one standard deviation of your mean. In this case, one standard deviation is 0.02. So let us consider our sampling distribution of p hat. Let us take all possible samples of size n equal to 400 and look at the distribution of the resulting p hat values. 95% of samples have cracking rates within 2 standard deviations of the mean. Think back to the rule I just mentioned. So that means between 0.2 minus 2 times 0.02, remember, one standard deviation is 0.02, so 2 standard deviations would be within our 95%. So this implies that 95% of our samples should have a cracking rate between 16 and 24%. Our new rate was 17%. So is this enough evidence that the cracking rate has really changed? Well, this brings us to our knowledge of our normal model and applications of our central limit theorem. So we can have an observed cracking rate of 0.17, which is 0.03 away from our null rate of 0.2. So we must ask ourselves, what is the probability of taking a sample that results in a cracking rate 0.03 or more away from the null rate of 0.2? This would be indicating how rare our observed rate is. The probability is 0.067 in each tail, or in other words, 13% total. So our conclusion for this problem, a sample of 400 ingots with a cracking rate this far from 0.2 would happen about 13% of the time just by chance. That doesn't seem very unusual. This means our observed proportion of 0.17 doesn't provide strong evidence that the new method changed the cracking rate from 0.20. So for us, when we are conducting a hypothesis test, we have really just 2 options for conclusions. We reject our null hypothesis, which means that there is enough evidence to support the alternative hypothesis, or we do not reject the null hypothesis. This means there is not enough evidence to support the alternative hypothesis. In our ingot example, we did not reject the null hypothesis because there was not enough evidence to say that new method was significantly better than the original method. Something that is very, very, very important for you guys to know and understand, because it is a common mistake, accepting the null hypothesis is not an option ever. We are not going to say that the null hypothesis is true, and we are not proving anything. We can either reject or do not reject the null hypothesis. We never accept it. Let's take a look at an analogy using the legal system. What is the null hypothesis? Well, in the legal system, a null hypothesis would be guilty. The alternative hypothesis is not guilty. Notice that innocent is not an option. You are either proven guilty or not guilty. Next, we need to talk about what does it mean to have enough evidence. You'll notice I've used the term significance a lot. Well, the level of significance is actually denoted by alpha. You've seen that value before. And this specifies how much evidence we require against the null hypothesis to reject it. The smaller the value of alpha, the stronger we require the evidence to be. The most common is alpha equal to 0.05. This alpha that we're speaking about now is the same alpha you're used to us talking about when we were constructing the 95% confidence interval. So an alpha of 0.05 would be equivalent to a 95% confidence interval. So what is it to be something statistically significant? Well, if we reject our null hypothesis after choosing a significance level alpha, we say the result is statistically significant at the alpha level. We also say that the null hypothesis is rejected at the alpha level. So oftentimes when we're saying our interpretations for our hypothesis test, we will say we reject the null hypothesis at alpha equals 0.05. Or we alternatively will say we reject the null hypothesis. We are at a 5% significance level of confidence that the true proportion is different than our hypothesized value. Now, brings us to the next logical question. How do we make that decision of significance? Well, there's two methods of doing this. First, we can use the critical region method, or we can do the p-value method. This brings us to our third objective, defining a p-value. So what is a p-value? The p-value is the probability of selecting a sample at least as extreme as the observed sample, assuming that the null hypothesis is true. We did the p-value method in our example, roughly. If our p-value is very low, either the null hypothesis is not true or something remarkable occurred. If the p-value is high, the data are consistent with the model and the null hypothesis. Let me remind you, the p-value is a probability. So that means our p-value is going to be between 0 and 1. So if something is close to 1, that means it's high. If something's close to 0, that means it's low. Now, high and low are kind of vague terms. So what do we mean by it being high or low? Well, let's consider our level of significance alpha. If our p-value is less than or equal to alpha, that means we can reject our null hypothesis. Again, scrolling up, so we are told that if the p-value is low, either the null hypothesis is not true or something remarkable occurred. So very low means it is less than or equal to alpha. So that is, if our p-value is less than or equal to alpha, we reject the null hypothesis. The result is statistically significant at the alpha level of significance. Ideally, when we are conducting a hypothesis test, we want to reject the null hypothesis. Ideally, our p-value is less than or equal to alpha. Think about our ingot example. If we've implemented a new process, we're obviously going to want that process to be better because implementing a new process costs time and money. It would be a disappointment for us to have the results that we did, which is where we did not reject the null hypothesis. We did not have statistical significance at the alpha level. So, speaking of our ingot example, we talked about what happened when p-value was less than or equal to alpha. Well, conversely, if our p-value is greater than alpha, then we do not reject the null hypothesis. Again, formally stated, if the p-value is greater than alpha, we do not reject the null hypothesis, and the result is not statistically significant at the alpha level of significance. Now, as I alluded to earlier, all of our hypotheses are two lines. The first line is the null hypothesis. The second line is the alternative hypothesis. The null hypothesis is an equivalence statement. Our H naught colon our parameter equals our hypothesized value. Your alternative hypothesis is going to be almost identical to your null hypothesis. The only difference is the sign. Now, this sign in your alternative hypothesis has three options: do not equal to, greater than, or less than. These are known as right, left, and two-tailed test. So, if our null hypothesis asks us for simply a difference or greater than less than situation, that is a two-tailed hypothesis, and we would write it using, say, our ingot example, H naught colon P equals 0.20 versus H1 colon P does not equal 0.20. If we are told that we wanted our parameter ideally to be larger, that is a right-tailed, one-sided test. And in our ingot example, we would write our hypothesis as H naught colon P equal to 0.20 versus the alternative H1 colon P greater than 0.20. And on the other end, if we were wanting to conduct a left-tailed one-sided test, we would be using less than in our alternative hypothesis. So for example, with our ingots, the null hypothesis would be H naught colon P equal to 0.20 versus the alternative hypothesis H1 colon P less than 0.20. Let's take a look at an example, identifying the hypothesis. The manufacturer of a new model of hybrid car advertises that the mean fuel consumption is equal to 62 miles per gallon on the highway. A consumer group claims that the mean is less than 62 miles per gallon. Now, notice that we were talking about means, not proportions in this situation. So that means our parameter of interest is going to be mu. And the hypothesized value in this case was 62 miles. Putting our information together, we can write our null hypothesis, H naught colon mu equal to 62 miles. Now we can move on to writing our alternative hypothesis. H naught colon mu, we'll leave our symbol blank for now, 62. Deciding what symbol we should use, whether not equal to, greater than, or less than, comes straight from our problem. it states that a consumer group claims that the mean is less than. That means we should use the less than sign. So our alternative hypothesis should be H1 colon mu less than 62. Let's take a look at a second one. The Ohio Department of Health claims the average stay in Ohio hospitals after giving birth is greater than the national mean of 2.0 days. Okay, so once again, we are talking about means and averages. So that means our parameter of interest is going to be mu for both our null and our alternative hypothesis. For our null hypothesis, we know our sign is 0. Next, we need to consider what is our hypothesized value. Well, our supposed hypothesized value is what our national mean is, which is that 2.0 days. Now, let's reread the problem in order to get our alternative hypothesized sign. So it says that the Ohio Department of Health claims that the average stay in Ohio hospitals after childbirth is greater than. So that's going to imply we use the greater than symbol, and then we will use the same hypothesized value of 2.0. We can check our answers on the next slide. This is just so you have it written out. Hopefully, this is starting to come a little bit easier to you. Let's take a look at a third example. A wildlife biologist working in the African savanna claims that the actual proportion of female zebras in the region is different from the accepted proportion of 50%. Okay, so to begin, we know we are going to have a null and an alternative hypothesis. So we can set that up immediately. Next, we care about our parameter of interest. Are we talking about proportions or means in this situation? Well, in this problem, I've seen the word proportion twice. So that's going to tell me that our parameter of interest is going to be P for proportion. Focusing on our null hypothesis, I know the sign is going to then be equal. Next, we must examine our hypothesized value. Well, it is pretty convenient that the only value given into the problem is that 50%. And as it is 50% in the null, it must be 50% in the alternative. Our last step is identifying what sign we need to use in the alternative hypothesis. Let's read the problem and see if we can't figure it out. A wildlife biologist working in the African savanna claims that the actual proportion of female zebras in the region is different from the accepted proportion of 50%. The key word here is different. Notice it doesn't say less than, greater than, it just says different. That implies that it could be either less than or greater than. In this case, that means we need to use the symbol not equal to, because we don't know what direction that our female zebra proportions are going to go in. We can check our answer on the next slide. Very good. Looks like we did it right. Let's do one more example. Boxes of a certain kind of cereal are labeled as containing 20 ounces of cereal. An inspector thinks the mean weight may be less than this. Once again, we'll start by writing out our null and our alternative hypothesis. In this case, are we talking about averages or proportions? Well, I see the word mean, so that's going to tell me our parameter of interest is going to be mu. for alternative, we don't know the sign yet, but for the null, we know that it's going to be equal. Reading our first line again, it says boxes of a certain kind of cereal are labeled as containing 20 ounces. So I'm going to take that to imply that the mean should be 20. The inspector thinks the mean weight may be less than this. That is going to be our alternative, less than. Hopefully at this point, this is feeling pretty easy to you. We can again double check, looks good. Okay. Now let's take a look at an example 5. This one's going to be a little bit different. This is going to begin using our p-value. A restaurant owner claims the mean amount spent by diners at his restaurant is more than $30. A test is made out of a hypothesis of null hypothesis of mu equals 30 versus the alternative of mu greater than 30. The resulting p-value, is 0.16 at the 5% significance level. So, which of our 4 options is correct? A, we should reject the null hypothesis. We do not have sufficient evidence to say that the mean amount is greater than 30. B, we reject the null hypothesis. We have sufficient evidence to say that the mean amount is greater than 30. C, we do not reject the null hypothesis. We do not have sufficient evidence to say that the mean amount is greater than 30. Or D, do not reject the null hypothesis. We have a sufficient evidence to say that the mean amount is greater than 30. Okay, so let's take a look. If we recall, our rule is that we will reject our null hypothesis if P is less than or equal to alpha. Our p-value is 0.16. Our alpha value is 0.05. Is 0.16 less than or equal to 0.05? No, it is not. So this means we are going to not reject the null hypothesis. This will eliminate options A and B. Our first line in C and D are the same. Do not reject the null hypothesis. Next, we have to worry about our second statement. Our second statements are almost, the same. The only difference is whether we have or have not sufficient evidence. Notice our null hypothesis says things are equivalent. The alternative hypothesis says things are greater than. We have not rejected the null hypothesis. The null hypothesis says things are the same. This means we do not have sufficient evidence to say that the mean amount is greater than $30. At this point, I want to give you a hint for that second line going forward. If you reject your null hypothesis, that is going to imply that you have sufficient evidence of your alternative. If you do not reject your null hypothesis, that is going to imply that you do not have sufficient evidence of your alternative hypothesis. This might be something that you want to memorize going forward. Okay, so this brings us to our fourth objective, type 1 and type 2 errors. So in hypothesis testing, there are 2 types of errors that we focus on, type 1 and type 2. if we think of all of our possible options of rejecting the null hypothesis and not rejecting of the null hypothesis, we have 4 options. Either the null hypothesis is true or the null hypothesis is false. That is the truth. Next comes the step of our decision. We will decide to either reject the null hypothesis or not to reject the null hypothesis. Ideally, when the null hypothesis is true, we will make the decision to not reject the null hypothesis. If we make an incorrect decision, that is when a type 1 error occurs. When the null hypothesis is true, but we reject it. So again, the reality is that the null hypothesis is true, but we as statisticians tell the world it's false. The second option for truth is to state that the alternative hypothesis is true. Ideally, when the alternative hypothesis is true, we will reject the null hypothesis. Because if we reject the null hypothesis, we're saying the alternative is true. That is a correct decision. But sometimes we make mistakes. So sometimes it occurs that the alternative hypothesis is true, but instead we make the decision to not reject the null hypothesis. This error is known as a type 2 error. A good way to, if you're asked to find, if you're given an example and you're asked to say which error could it possibly occur, if the truth is that the null hypothesis is true, it has to be the type 1 error. If the truth is that the alternative is true, it has to be the type 2 error. Same with the decision. If the null is true, but we reject it, type 1. If the alternative is true and we do not reject the null, that is a type 2 error. This might be another type of thing you should memorize. To help put this in example of the legal system, we can say that our null hypothesis is not guilty and our alternative hypothesis is guilty. Meaning that in the type 1 error case, the person is not guilty, but we send them to jail. A type 2 error would be that we let a guilty man or woman go free. Type 1 errors are considered to be worse than type 2 errors. The same in the legal system. Our legal system was designed that ideally a guilty man will go free before an innocent man is put into prison. Okay, so just at this point, let's formally define a type 1 error and a type 2 error. So type 1 error, that is when we have rejected the null hypothesis when the null hypothesis is true. Type 2 error is not rejecting the null hypothesis when the alternative hypothesis is true. If the null hypothesis is true, the probability of our type 1 error is alpha, our significance level. So when we give an alpha equals 0.05, what we're saying is that we want the probability of a type 1 error occurring to be at 5%. Or, well, no or, that's just it. Let's take a look at an example. A test is made of a null hypothesis where mu equals 5 versus an alternative hypothesis of mu being less than 5. The true value of mu is 5, and the null hypothesis is rejected. Which would be a correct, or rather, what is our options? Is this a correct decision, a type 1 error, or a type 2 error? Well, the first thing we should really ask ourselves, was a mistake made? Let's read the problem again. A test was made of our null hypothesis, mu equals 5, versus the alternative of h1 colon mu less than 5. The true value of mu is 5. Okay, so that's saying that the alternative, or not the alternative, I'm sorry, the null is true. And h naught is rejected. So the truth was that h naught is true. Our decision was that h naught is rejected. This means an error occurred. So our options of correct decision, type 1 or type 2, well, we can eliminate the possibility that this was a correct decision. Now we need to identify whether this is a type 1 or a type 2 error. Well, if you don't remember, we can scroll up to our previous slide. Type 1 error is rejecting the null hypothesis when the null hypothesis is true. The type 2 error is not rejecting the null hypothesis when the alternative hypothesis is true. Well, we rejected the null hypothesis and the null hypothesis is true. That implies we did a type 1 error. Very good. Let's take a look at a second example, although this would be our 7th example of this lecture. A test is made of the null hypothesis of mu equals 45 versus the alternative of mu less than 45. The true value of mu is 40, and the null hypothesis is rejected. We want to know, is this a correct decision, a type 1 error, or a type 2 error? Well, let's think about it. We have the truth, and we have the decision. Ideally, the truth and the decision match. If not, we have an error. The truth is that mu equals 40. Or in other words, the truth is that we should reject the null hypothesis because 40 is less than 45. So the truth is that the null is false. Our decision was that the null should be rejected. To make this easier, I'm going to change the word null to h naught just to keep it consistent because I do know you guys are learning this for the first time. So we wrote the truth that null is false. Our decision was that the null is rejected. This implies we made a correct decision. The null was not true, and thus we rejected it. Good job, us. Let's take a look at example 8. A test was made of the null hypothesis mu equals 63 versus the alternative mu is greater than 63. The true value of mu is 75, and the null hypothesis is not rejected. So the truth, well, if mu is 75, that is greater than 63. So that means our null is false. Our decision was that h naught is not rejected. Well, unlike in example 7, when h naught was false, We did not reject. So this eliminates us making a correct decision. So did we make a type 1 error or a type 2 error? Well, if we scroll back, a type 1 error was when the null is true, but the null is rejected. We have the opposite situation. So this is going to be a type 2 error. The truth is that the null is false, but we failed to reject it. Okay. Let's take a look at one last example. A test is made of the null hypothesis of mu equals 20 versus the alternative of mu not equal to 20. The true value of mu is 25, and the null hypothesis is rejected. And again, we want to determine if this is a correct decision, a type 1 error, or a type 2 error. The truth is that the null is false because mu equal to 25 is going to fall in line with the alternative hypothesis. So again, our null is false. That is the truth. Our decision was that our null is rejected. Truth, null is false. Decision, null is rejected. That seems to me to be the correct decision. It wasn't true, and we rejected it as true. Very good. Okay, so this brings us to the end of the lecture. Let's take a quick summary of what we learned. We learned that we can use hypothesis testing to test claims about a population parameter, specifically mu and p, or proportion and mean. We learned how to base things on a sample, and we want to find the probability of getting our sample or something more extreme if our null hypothesis is really true. Okay, that's it for this lecture. As always, if you have a question, send me an email. Have a good night.